Hello, hi. So we are going to talk about today's um, daily challenge, coding challenge in Leetcode actually. So it's 31st of um, December. So the last question we have for this month is largest rectangle in histogram. So it's a very um, interesting problem, I would say. It's quite special in some way, and then it's kind of hard to do as well. The algorithm is not really easy to think of. I think it's a quite interesting problem. So I would say uh, so the question is asking you that given a list of numbers representing the height of the bar of each bar in a histogram. So you are asked to find the largest rectangle you can find. You can find in the rectangle in the histogram and return the area of that rectangle. So for example, this is 2 1 5 6 2 3. So each bar is with height. The width of that is 1, and then you're asking you're asked to return the result of the largest rectangle you can find in this histogram, and then you are asked to return that area. So here it's 5 6. It's this area that's shadowed, so it's 10. So the height is 5 and then the width is 2, so that's 10. So you cannot find any larger one. For example, if you think of this one, so 1 1 1 1 1 1, so that's only 1 2 3 4 5 6, so that's only 6 in area. If you look at this one, so that's only 3. That's and then if you include these two, then it give you like 4. And then basically the the thing here is like you cannot find anything larger than this shadowed rectangle, and then you are asked to return to this. You are asked to return this area actually. So how to do this? So I will give you a little different example that's a little bit different, but I think like it's more representative than the example before. But a very naive way to do this, I would think, is to, for example, if I have these as an example, so what I will do is to say, to imagine there's a bar here, starting from here, and then I move it by one unit at a time. So I move it to here, and then I look to the right, to the left of my bar to say what's the largest rectangle I can form uh, before this bar actually. So for example, if my bar is here, there's only one, then I form a bar, I form a rectangle like this. And then if I move my bar here, there's you iterate from here this bar to the left, and then you have two choices. So you have one is to have this rectangle here, or the other choice is to have the rectangle like this actually, right? So you can do this in ON2 squared. So you can have a easily you can have ON squared algorithm to say I have a bar here and I'm traversing. I have a like a so I'm using these as my right boundary. So I'm using these as my right boundary, and then I'm just checking what for each left boundary I have before me, what's my total area? What's a total area I can achieve using these two boundary? And then you can do this iteratively, so you can have two for loops, which is quite easy to do actually. So this is definitely something we can try, and I think like it's a naive algorithm which works apparently. So definitely I think it's something worth trying. But so usually like ON2 it's not really a very efficient algorithm actually. So in an interview setting, if you have a ON2 squared ON2 ON squared algorithm, you need to think about like if there's any chance I can do better than this, if it's O log n or like a O n log n. So something better might be O n log n, and then or on even like in this case, like do they exist? Can we do better than that? So I think that's quite interesting actually. So like I think there's definitely some way we can achieve on in this scenario. So like I think this one is definitely achievable. So but with some like a logic and with some like smart tricks, you can achieve this from to go from here to here actually. So how do we do that? So before we go into the detail of how do we go from n squared to on, let's think about like let's look at one particular example on how to calculate the area actually. So suppose we have the right boundary here at this bar, and we have the left boundary here at this bar actually. So we denote the each boundary using its the using the the index of the bar right to that boundary. For example, left is 1, and right, although right is here, but we use the 3 index here to denote the boundary here. So the width of that of this of this rectangle here can be represented by 3 minus 1. That's easy to see, right? And then the height of the boundary is actually the minimum height of right minus 1. So it's this bar here, and the bar and the height of left, which is this bar. So you are going to find minimum of 3 and 2, and then you are going to find that height is 2, and then the area is equals to 4 actually. So that's the area here. So I just want to mention like how do we calculate the area, because that's quite important to the algorithm, to the implementation later. Now now let's think about how do we go from on squared to on. So that is so one thing you noticed when you are going through the area is like if you are going if you have a ascending bars actually. So like if your heights are increasing, so you will notice like when we do the original like naive algorithm, we are checking, for example, if we fix the right bar here, we are checking this rectangle first, then we are checking this rectangle first, and then we are checking these rectangles at last. But this rectangle, I want to emphasize on this rectangle actually. So if I can change a color and then use it here. So this rectangle, so this 2 by 2 rectangle is definitely larger than this rectangle, this 2 by 1 rectangle, right? Like it's definitely like that's something you are, or this is very obvious. But this 2 by 1 rectangle is checked when you fix your right bar here actually. So you see we are doing like a repeated work. So we already checked so we know that this rectangle is definitely larger than this like smaller rectangle. So why bother to check this rectangle's area when we can just when we know that this one is going to be larger than that? So that's the information. That's the information that can make your algorithm go from on squared to on. Is if you ever find increasing height, the bars are going the bars heights are increasing, you can be guaranteed that if you fix your right area, your right bar at the highest one, at the one that's the last bar of the ascending bars, then you can guarantee that if you move your left bar like this, then you are guaranteed that you don't need to check this bar, right? Like you just need to say my left bar is here, so I know my rectangle is this one. And then my left bar is here. Then I can check this one, and this one is definitely larger than the smaller one, which I don't need to check actually. So basically, what the question becomes finding the highest bar before in a ascending bar array, and use that bar as a basis as your right bar, and then go through the left bar, go through the bars that's lower than you before you, and then checking the area of each rectangle, each of the largest rectangle you can form with these left bar and right bar, and then updating your result. That's basically the question is about actually. So how do we do that? How do we achieve that? That's something. So that's something like we need to we need to think about in the next step actually. But I think like if you can pause here for a minute and then do something, do some like a sketching, and then do like use a pen and paper and see. The idea is just finding the right bar, finding the correct right bar, and then go left. Then you avoid doing like a repeated work actually. So that's the whole basic idea here. So now we have this core idea we have, right? Like is to how do we solve this problem, which is basically what we need to do is to find the ascending array of bars and use the largest one. So use this one as the right boundary, and then go left and try to find the largest area it can achieve, which is this one, either this one or this one or this one, right? So it needs to be able to do that. And then similar to here, like it needs to go from it use another right bar here, and then it goes left, and then it comes to here, and then it comes. So basically, the idea is like this. So how do you do this? How do you actually do this? So basically, you are going to need to use a thing called monotone array, the monotone stack, or monotonic stack actually, to find the ascending array and then go left. So basically, the idea. This is something like you might not know actually. So like, but it's basically uses array to try a stack to track like what's ascending, and then once you hit the descending thing, descending array thing, descending element that's going that's break this property, you need to go. Then you need to pop out the elements, and then find the area actually. So this is a pattern, I would say, like it's like something like a dynamic programming or dynamic search, which can be quite useful to solve this kind of problem. Like there's a couple of questions which are quite special, or like using which will utilize this this property or this data structure or this pattern. I will make a video later to talk about this a little bit because this is not covered in like most of the algorithm or data structure textbook, but I think it's quite interesting thing pattern to use actually. So before we go into the details of how this work, I would say I would say I would think I would say there are some like boundary things you need to concern yourself about. So there's a trick here actually, which is to add another element to the array. Put it here, and then has 0 actually. So later you will see why this is useful. But for now, you just need to know like there should be an array of zero heights of zero, and then there like it will become very handy later if when we work through the algorithm. But for now, you just need to know like you have to place a zero here, which like vastly simplify your algorithm. So back to the monotone stack, like how does it work? So basically, what you do is something like this. You have so let me write this down. So you basically initialize your stack. You will need a stack, right? Like basically initialize your stack, and then you have some popped elements. So like at some point you need to pop out stuff from the element. You have a right boundary defined by something, and then you have a left boundary defined by something, right? Like I will go into detail of like what's right and left here, and then you will have a height, and with the right boundary, left boundary, and height, like we mentioned before, you can calculate the area, right? So that's what's going on actually. So like so if you place your stack, so like you initialize the stack are like filled with the index here 0, 1, 2, 3, 4, 5, and then you can put your stack. You initialize that stack with -1, which is this element actually, which is 6. Right, like it's 6, but it's also -1 in Python. It's the last element, and then you go through this this array. So it becomes so if it's larger than if this element is larger than whatever is on top of the stack actually. So like if your height you have a pointer, right? Let's call it I. If your height I is larger than height stack -1, then what you are doing is effectively, then what you need to do is effectively adding the index to the array actually. So it becomes so 1 to 3, then it becomes -1, 0, 1, 2, right? So like let's write it properly. So like it becomes 1, 2, and now you have encountered 3. So 3 is smaller than so 1 is smaller than 3, right? So now it's the time you pop out the element from the stack, and then move it to the popped, right? And then your right boundary is defined by this thing is 3, right? Then the last, right? The left boundary here is defined by whatever is on top of the stack, right? So that becomes 1. And your height is basically like whatever you have popped already. So it's height. That this thing is height popped. So it becomes this one. So that's 3. Your area becomes 3. So which is this height times 3, which is your right boundary minus your left boundary. Notice that here you need to -1 again, because like 3 minus 1 equals 2, right? But you need this, right? You need this area. So that's 1. So basically it becomes 3. So now you have this this is you have found this one. So now you effectively fix your right, and then you go left, right? Then you go left again. Your left boundary needs to be moved again. How do you do that? It's you find that 2 is still larger than 1, right? So you basically move this to 1. Move this 1 out, and your right boundary is 3. Your left boundary becomes 0, right? And then your height is determined by this what you have popped out, let's draw out this thing we are looking at actually. So let's increase our brush size a little bit. So it's basically this area. So your height is 2, and then the width is, so basically your area becomes 2 times 3 minus 2 minus 1. So this sorry, sorry, this should be 0. So this becomes 2 by 2, which is 4, which is this area, right? And then you can continue to say 1. 1 is not like a, it's still quite it's not smaller than 1, right? It's not smaller than 1. Then you need to pop it out again. It might becomes minus 1. So pop will becomes 0. And then your r equals 3, right? You're still fixed here. And then your left boundary becomes here, right? Like it becomes minus 1 basically, which is the last element here. And then your height becomes to 1, which is this determined by this height, right? And then your area becomes 1 times 3 minus 1, right? So like it becomes 3. So basically this is 1, this is 3. So it becomes 3 again. So I'm only going to cover this part actually. But I think it's good for you to actually get a pen and paper out and try this algorithm on this part as well, to continue this table, and then you will see how it works in general. So the key idea is to find ascending array, use this as the right boundary, and then go left to find the left for each boundary to find the largest array it can form actually. So for example, 1/4, it's still the same thing. I need to find my left boundary is here, and then I need to find my left boundary is here. Then my area is 4. But if my left boundary becomes here, then it becomes like 1 times 2 becomes 2, right? So that's the largest form I can come largest array I can form. But why, you may ask, why not, like, why, if your right boundary is fixed at 5, for example, why not like go further left? That may form a thing that's larger than like whatever you have 4 here, right? That comes back to the previous point. It's like you know for sure that like nothing here will form a larger rectangle. That's because all these things, all these heights, so they cannot, like, you cannot, even if this here is 3, you cannot form anything larger than 4. Larger than your height is determined by this 1 down below, right? So like you cannot form anything larger than higher than this 1. So there's no need to go back. So that's the idea here. Like if you check the previous one, then you know like basically you are saving yourself from doing repeated work here. So the similar idea goes here. So you move the right point, your right point here, right boundary here, and then you check again until this point, I think. And the question, the interesting thing is like you, after this, you still need to move your right boundary to the fictional, like the element we added here, 0, and then you need to go back to see if there's any form thing you can form with this boundary, right? Like, but there's none because this is 0, so you don't need to do that. So basically, I'd suggest you to take a pen and paper out and work out like how this algorithm work and how it saves you from doing repeated work actually, and convince yourself to do that. That's a key part actually. So now we have this in mind. we can look at the implementation, which is quite easy to explain then. So basically you are doing whatever being said over the in this section actually. So you initialize your stack equals to -1. Your result becomes you set your result to be 0, and then you append 0 to the height, which is doing this part, like doing which is doing this part. So now, what for the things in this array, you just need to say if while there's something in the stack, and my the element in my in the stack the stack the height that's pointed by the last element in the stack is higher than me, then I will just pop out which is the height I will be using, and the width is like the left boundary, and then the boundary. So this is I will be my right boundary. Stack -1 will be my left boundary, and -1 will be my width, and then my result will become max result height times width, height times width, right? Then you can find your largest result this way, and then you can append your stack here. So if you run this algorithm actually with the example we have, then it gives you the correct result. If you run it with this algorithm, it will also have the correct result actually. And if you do submit, you see it will have the correct answer as well. So I hope like this question, I understand like there are some points where I deliberately left out actually. So I didn't really finish the whole demonstration here, but that's on purpose. I want you to take out a pen and paper and try to convince yourself that this algorithm actually first it works, and then actually it saves you doing repeated work actually. So if you can convince yourself that, then I think this you understand the whole why do we like want to fix the right boundary and go left. Why do we think like using a monotone stack can help in this situation? So if you can try that, and then let me know what's your thoughts. If you find like anything not clear enough, and then I can make another video to go through this in more details, and then and try to convince you. But I think it's better if you take out a pen and paper and try to convince and try this yourself. I think that's a key part of this exercise. So thank you very much. Please comment and subscribe.